Hi everyone, I'm Arun Narenthiran from the University of Illinois, and I'm presenting our work CropFollow++, a robust under-canopy navigation system with Keypoints. Under-canopy agricultural robots are compact robots that traverse the tight space between the crop rows below the plant canopy. They can enable various applications such as precise crop monitoring, weeding, spraying, and cover crop planting throughout the growing season, which is not possible with over-the-canopy equipment like tractors. Under-canopy agricultural navigation is challenging due to various factors such as unreliable GPS because of multipath error, noise in LiDAR scans, lots of occlusion and clutter, large variability in appearance of soil and crops, and small margin for error due to the tight space available to navigate. To address these challenges, we've developed a modular, interpretable, and anomaly-aware under-canopy navigation system with semantic key points representation called CropFollow++. It considerably outperforms the prior state-of-the-art for visual under-canopy navigation that used end-to-end perception learning architecture. We also deployed CropFollow++ over 25 kilometers on multiple under-canopy cover crop planting robots, and we discussed the failure modes observed during this. Here's an overview of CropFollow++. We trained a convolutional neural network with supervised learning to predict 3 semantic key points of interest that represent the vertices of the triangle formed by the crop rows on the image. These 3 key points are predicted as heat maps. The 3 key points are extracted from the heat maps using spatial argmax operation. Then by using the role estimation of the robot from IMU and the known camera intrinsics, the 2 states representing the angle and position of the robot relative to the crop rows are calculated. These 2 states are used to define the reference line that is in the middle of the lane relative to the robot. A model predictive controller is used to steer the robot towards the reference line by controlling the linear and angular velocity. During deployment, we use 2 heuristics to detect outlier predictions of key points. The variance of the vanishing point heat map enables detecting anomalous scenarios such as occlusions and collision with corn plants. In addition, we check the geometric properties of the triangle to filter the outliers in the bottom 2 key points. We evaluated our key point-based perception system in CropFollow++ with the end-to-end perception system in CropFollow that directly predicts heading and distance ratio. We use mean and median L1 error in heading and distance ratio as the evaluation metric. We evaluated on 3 cases using the entire validation set, a subset representing images from zigzag trajectories that contain large variation in viewpoints, and a subset representing images from trajectories in which the robot was traversing on uneven terrain. We can see that our key point representation in CropFollow++ has considerably lesser median L1 error in both heading and distance ratio in all cases. This indicates that our key point representation is able to more accurately predict the row geometry of crops than the end-to-end representation. We perform comparisons between the semantic key point representation in CropFollow++ and the end-to-end perception in CropFollow in different field conditions. We use the same controller for both cases. We report the number of collisions and the maximum distance traveled without collision as metrics. We can see that CropFollow++ encountered considerably lesser number of collisions on average and also traveled farther between collisions across all runs. In this video, we show a visualization of the predicted key points when the robot was successfully navigating in a cornfield. Our heuristic checks were used to filter the outliers that we observe in some of the frames. We deployed CropFollow++ on multiple robots over large distances for the application of under-canopy cover crop planting. Compared to aerial seeding with drones or planting cover crops with tractors after harvesting corn, our system minimizes wastage of seeds and enables more biomass of cover crops by planting earlier in the season. During this large-scale deployment of cover crop planting robots, we added an autonomous collision detection and failure recovery module to minimize the number of human interventions needed. The collisions are detected by comparing the applied velocity and estimated velocity of the robot. And whenever a collision is detected, it triggers the failure recovery module that uses the rear camera to recover, as we saw in this video. The human intervention is needed only in case of irrecoverable failures. We deployed CropFollow++ for about 25 kilometers in total, and this resulted in 109 collisions. Of these, the robot recovered autonomously from 76 collisions, and the remaining 33 irrecoverable collisions needed human intervention. We show the various causes that led to irrecoverable collisions in this pie chart. Large gaps in cornrows, significant occlusion due to weeds, and the prediction error in viewpoints very close to the cornrows are the main failure modes. Here, we show the visualization of failure due to gaps in cornrows and in cases where there is significant occlusion from weeds. So in summary, we have demonstrated a robust under-canopy navigation system with semantic key point based perception, and we deployed this over large distances. Our system enables a novel application of under-canopy cover crop planting that can improve the soil health and sustainability of row cropping systems. Thank you, and feel free to reach out if you have any questions.